All right, this video is going to start unpacking some of the more difficult concepts with probability, conditional probability, and then whether events are independent or dependent. I included some information here from the text. So conditional probability of A given B is written in this notation here. So I know that B has happened, and I want to know, okay, now what's the probability that A happens since I know B has already happened? That conditional piece reduces your sample space. So you're only looking out of the probability that A and B have happened out of the outcomes of B. If you go back to our Venn diagram example, given B has happened means I know that I have to be in this circle. And then I want to know from there, what's the probability that A happens? So I'm looking at this intersection out of just the outcomes of B. Here is an example for you. If you have a sample space of 1 through 6, and A is 2 or 3, and B is 2, 4, or 6, and we know that B has happened, so 3 out of those 6 happens. What's the probability that 1 or 3 happens? That outcome is going to end up being 1/3, and you can see mathematically why that is the case down here. Now, 2 events are independent if, when you consider that conditional probability, and it does not actually matter that B has happened, A is just going to happen no matter what. Similarly, it doesn't matter if A has happened, it might just be the probability of B, like it resets every single time. And if 2 events are independent, then it's true that the probability of A and B happening, that you can multiply them together. We're going to talk about this with terms of replacement and without replacement. So if you do replace things, then you assume that with that replacement that you are resetting the probability each and every time, and those events are considered to then be independent. If you do not replace and you have a really small sample size, then we would consider those to be dependent events. And you would have to show or have good reason to show that A and B are independent, and you assume they're dependent unless you can show that otherwise. Now, where this becomes a little bit negligible is when you have a really big sample. So if you're sampling of size 10 and you're choosing things out of that sample of size 10, well, then it does matter if you have like 1 out of 10 versus 1 out of 9. Like those are different numbers proportionally to each other, like fraction wise. But if I'm selecting out of like 100,000 and I'm selecting things, and even if I don't have replacement here, as a fraction, these two are so close to each other that we can just assume independence because we're choosing from such a large sampling frame that choosing one and then changing the denominator to choose the next one isn't really mathematically that different. Okay, so sample size does kind of take a play on whether you want to consider independence or not. So let's say there's a box and it has 3 balls in it. 2 are white and 1 is red. It's just going to be purple. That's going to be fine. Okay, we select 1 ball, we put it back in the box, so we are sampling with replacement. Let's go through and you choose 1 ball and then a second ball. So let's look at what happens. We have 2 choices, right? We have white and we have red, and those are not equally likely. White is 2/3, red is 1/3. Then I replace and I have a second choice. And those probabilities reset when I do that. All right, so if T is the probability of getting the white ball twice, well, then I have to go up this tree branch and then this tree branch. Again, since these are independent events, the probability of getting white and white, I can just multiply those two probabilities times each other. Probability of F, this was T up there, probability of F is getting a white ball on the first draw. Well, that's just 2/3. Probability of S is probability getting a white ball on the second draw. Now this is a little bit tricky because I actually have two pathways. We said that combination was 4/9, but I could also have this pathway and technically have, let's see, that's 2/9 if I multiply. Those are both outcomes of having white for the second ball. So I would be able to say like, okay, well, this pathway gives me 4/9 and this gives me 2/9. If I continue with all of this, this is also 2/9 and this is also, or this is 1/9. So you can see this is where 9/9, like all four of the outcomes come to play here. But these are the two outcomes that I want. So I'm going to say that that is 6/9, or 6 of the chances out of the possible 9 have white second. All right, here, this is the probability of S given F. Well, the probability of S given F in the equation is the probability of S and F over the probability of F. If you remember, that's our formula that we had up here at the beginning. Well, I calculated some of those up here. Well, the probability of S and F, these are independent events, so that's going to be 6/9 times 2/3 over the probability of F, which we said is 2/3. Well, those cancel, and I'm just left with 6/9, which makes sense because these are independent events, so it should just be the probability of S. We can do this on the flip side as well, just to get comfortable with that formula. So we do the S and F. They're independent, so I can multiply over the probability of S. Those cancel, and I'm left with 2/3 here as well. Now, how would these probabilities change if the first ball was chosen with no replacement? Well, now our probability would change on that second one. Now our second probabilities would change. So if I already have the white, then these then change to 1/2, 1/2. If I have the red, well, then choosing the white, there's only 2 left out of the 2, and 0 left out of the 2 are red. So that's how those probabilities would change if there was no replacement. So you can organize your data in this way with these conditional probabilities of first turn, second turn, and see that replacement, non-replacement, or independent, dependent piece. All right, here's some verifying independence. So let's say that G is taking a math class and H is taking a science class, and H and G together are taking both. So I know these probabilities and I want to know, are they independent? Well, remember, if two events are independent, then this should be true based on our formula. So is 0.3, is that equal to 0.6 times 0.5? Well, half of 0.6 would be 0.3. So yes, these are independent, and that's the way that you can check using the formula that those two events are independent from each other. All right, let's look at one more example with conditional probabilities here and some independence. So in a particular college class, 60% of the students are female. 50% of all students in the class have long hair. 45% of the students are female and have long hair. Of the female students, 75% have long hair. Let F be female, L be long hair. One student is picked at random. Are these things independent from each other? All right, well, all we need to look at is probability of female and having long hair. Is that equal to the probability of female and the probability of times probability of long hair? Be careful here because this says 45% of the students are female and have long hair. So that 0.45 goes here. 60% are female and 50% of all students, 50, I started multiplying, 50% have long hair. Well, that's equal to 0.3. That is not equal to 0.45. So these are not independent of each other. Now, where students will get confused is this part right here. That's a conditional piece. So let's just add, it's not part of this problem, but I just want to add a little piece to this. I might be able to split this into conditional probabilities, and that of the females is important. So 0.60, which means males would have to be 40. Of the female students, 75% have long hair, so 25 do not. And so I could multiply up these branches to find the probability of long hair. Oops. Given female gives me that, but I could multiply up these branches as well to find this probability of long hair and female. And the reason is because remember this equation is this right here. And so if I multiply the probability of long hair given female by the probability of female, then I can find this right here. So when we multiply up our branches, we're finding that and probability. And so if I do 0.6 times 0.75, I get 0.45. Now remember it says that 45% of these are female and have long hair. So I already saw that and I'm checking it off right there. Now 50% of all students in the class have long hair. So when I think about long and no, I know that male and long, let me scroll down just a little bit, give me a little more room. Male and long is going to have to be the other part of that 50%. So if I need to find the probability of long given male, I know that that's the and probability over male, or 0.05 over 0.4. Gives me 0.125, and then I can go ahead and just subtract that from 1 to find this piece right here. And then that gives us a full complete picture. That's just one other way that you can break up these probabilities, and we can practice this a little bit more in class to make sure that you can organize this data appropriately and get all of the answers you would need to find the probabilities that you would want to calculate.